Hello everyone, so today we're going to be learning about polynomials and visualizing the graphs of cubic functions. So the question that I'm going to discuss is actually quite interesting. Unless you've seen this before, this might seem as something new, right? It's quite interesting, it's quite new actually. And this question in itself is quite beautiful. And the problem solving idea is actually really nice because it involves like a little bit of graphs, some geometrical interpretation, along with kind of this algebra polynomials kind of a thing. But yeah, if you're really good with algebra, if you can know a lot of brute force methods, then you might really have a go at this using just simple brute force. But yeah, the solution that we're going to discuss is quite elegant. It's quite interesting, and we'll definitely learn a lot from it. So this is problem number 10 from the AIME in 2015. And in this video, we're going to be learning about polynomials, degree and factor theorems. Obviously, not the basics, more like the implementations of that in the problem. And after that, graphing cubic functions, which is probably going to be the takeaway from this video. And in that, we're going to discuss the general graphs of certain cubic functions and how obviously that relates to a given problem. And after that, we have certain book sessions for the AMC and AIME. And at the end, of course, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what have they given to us? So they've told us that let f of x be a third degree polynomial with real coefficients satisfying f1 is equal to f2, and all of these are in mods, right? It's in modulus. So f1, f2, f3, f5, f6, and f7, all with modulus signs, is equal to 12. And they've told us to find the modulus of f of 0. Now, this is quite interesting actually. So essentially when I look at this, what I think is that f1, f2, f3, f5, f6, and f7 can either be 12 or minus 12. We don't know what that is. So essentially, when you have this modulus, things might be a little bit tricky to deal with, especially when you talk about like roots of a polynomial and such things, right? So why not remove this modulus altogether? So what I'm going to do is I'm just going to square it. f1 whole square is equal to f2 whole square is equal to f3 whole square. And all of these terms are essentially equal to 144. And the reason I did this is because, mod x whole square is nothing but x squared. So essentially, you can remove the modulus sign by this. So now what I can write is that f of x whole square minus 144 is equal to 0 has how many? 1, 2, 3, 4, 5, 6. 6 roots. And the 6 roots are x equals to 1, 2, 3, 5, 6, and 7, right? It has these 6 roots. It's pretty much clear. So via factor theorem, I can essentially write f of x whole squared minus 144 as c times x minus 1, x minus 2, x minus 3, x minus 5, x minus 6, and x minus 7. Because essentially, whenever I plug in any of these values into the right hand side, I get 0. It satisfies this equation. Right? So f of x whole square minus 144 is equal to this, essentially one of the forms of the factor equation. Now, essentially, f of x has degree 3. Right? So f of x whole square has degree 6. And that's pretty much clear, right? Because the right hand side also has degree 6. We have 6 linear terms in x multiplied to one another. So obviously the degree is 6. But now let's just do some analysis over here. Let's just do some analysis, right? Brief analysis. So if let's consider if f1 is equal to f2 is equal to f3 is equal to f5 is equal to 12. So let's say these 4 are 12, and let's say the rest of the guys f6 and f7 is equal to minus 12, for example. Essentially, I want to kind of consider the cases where 4 of these quantities are equal to 12 and 2 of them are equal to negative 12. So what really happens over here? So f of x minus 12 is equal to 0, has the roots x equals to 1, 2, 3, and 5. So again, kind of using a similar analogy, I can write f of x minus 12 as c times x minus 1, x minus 2, x minus 3 times x minus 5. In the question, they've explicitly given us that f of x is a third degree polynomial, right? So the degree of LHS is 3. The degree of right hand side is actually 4. We have 4 linear terms multiplied to one another. The degree is 4. Can a expression in degree 3 ever be equal to expression in degree 4? This is obviously untrue. So therefore, we can only see that only 3 of these things can be equal to 12 and the rest 3 will be minus 12. Right? So effectively, for example, For example, we can have f1 is equal to f6 is equal to f7 is equal to minus 12, and we can have f2 is equal to f3 is equal to f5 is equal to 12. This is a possibility. This is a possibility. We don't know if it's true or not, but this is a possibility. Essentially, any three of them will be 12, and the other three will be minus 12. And that essentially stems down from the fact that we just talked about above, that the degree of the left hand side and the right hand side need to be equal. So now that we figured out that three of them need to be 12 and three of them need to be minus 12, we move on to graphing cubics, right? So in general, okay, in general, if I just write f of x as a cubic, ax cubed plus bx squared plus cx plus d. So in general, a cubic function can have two types of graphs. In general, it can either look like this or it can look like this. And once you know this, once you kind of know this thing that it can either look like this or look like this, then things become like a lot easier. So let's analyze both of them via cases. So case one is if the graph of the cubic is like this, it's like this. Okay. So here, if I just draw like two lines, this is the line where y will be in minus 12, of course. This will be the line where y is equal to 12. And somewhere in the middle, we will have the x-axis where y is equal to 0. I'm not drawing the axis over here because I think that's pretty much clear. But essentially, somewhere between minus 12 and 12, we will have the line y is equal to 0 or the x-axis. So essentially, the points, the x-coordinates of the points on this line will all give value y is equal to 12 for the given cubic. And if I just kind of like write it, so for example, this comes before, right? This is 1, this is 2, this is 3, this is 4, this is 5, and sorry, not 4. In the question, like, what did you have? We had 1, 2, 3, 5, 6, and 7, right? Those were kind of the values. So 1, 2, 3, 5, 6, and 7. And if you're confused, like, why did I write it like this? Essentially, the smaller x needs to come before, right? So this point over here is coming before 2. Kind of like we just essentially mapping it on the coordinate axis. In fact, like to make it a little bit more clearer, I'll draw it like this. So essentially, let's say these points are giving y is equal to 12. This is obviously y is equal to 0. And these points is giving y is equal to minus 12. Figure not drawn to scale, of course. But essentially, it's something like this. It's something like this. What I've drawn over here is something like this. And obviously, all of these things I've included the negative x-axis as well. But here, the discussion is only in positive x because we have the points in positive x, right? x, 1, 2, 3, 5, 6, 7 are obviously positive coordinates. So essentially, here we can see that f1 is equal to f5 is equal to f6 is equal to 12, right? So f1 is equal to f5 is equal to f6 is equal to 12. And similarly, f2, f3, and f7 are minus 12, right? f2 is equal to f3 is equal to f7 is equal to minus 12. So I can write f of x minus 12 is equal to 0 has the roots x equals to 1, 5, and 6. Essentially, I can write f of x minus 12 as c times x minus 1, x minus 5, and x minus 6. And you can do that for f of x plus 12 as well, but it really doesn't matter. If I just plug in maybe like say, let's say put like x equals to 3 over here, I'll get f of 3 minus 12 is equal to c times 3 minus 1 is 2. This will be minus 2 and this will be minus 3. Now f of 3 is minus 12, right? F of 3 is minus 12. So minus 12 is negative 24 is equal to c times 3 to the 6 times 2. So this becomes negative 12. So c becomes essentially negative 2. And this is actually great because you actually figured out that f of x minus 12 is nothing but negative 2 times x minus 1, x minus 5 times x minus 6. So if I just plug in x equal to 0 over here, I'll get f of 0 minus 12 is equal to negative 2 times negative 1, negative 5, negative 6. So f of 0 minus 12, all four negative quantities is a positive quantity, and 32 is a 60. So f0 is 72. So modulus of f of 0 is 72. So this is essentially for this case, right? This is the case where the graph looks something like this. Let's say we analyze case number 2, right? Let's just look at the other case, case number 2. So case number 2 is obviously where the graph looks like this. It's kind of the other way around, right? And again, using the same ideology, this will be line where y is equal to 12, this will be y is equal to minus 12, somewhere in between we'll have y is equal to 0, right? Again, starting from the smaller x, this will be 1, this comes next, so this is 2, this comes next, this is 3, this comes next, so this is 5, this comes next, so this is 6, this comes next, so this is 7. So here I get f2 is equal to f3 is equal to f7 is equal to 12, and similarly f of 1 is equal to f of 5 is equal to f of 6 is equal to minus 12. So here I can again write f of x minus 12 is equal to 0, has the roots x equals to 1, 3 and 7. So essentially f of x minus 12 can be written as c times x minus 1, x minus 3 and x minus 7. Now if I just maybe put what shall we do? Oh sorry, not x equal to 1 actually. Here we'll have x equal to 2, right? Sorry for that. We have 2, 3 and 7, right? So it will be x minus 2. Now if I maybe put x equals to 1 over here, what will I get? I'll get f of 1 minus 12 is equal to c times negative 1, negative 2, negative 6. So essentially f of 1 minus 12 will be equal to, this will be negative 12c. Actually f of 1 is negative 12, right? So negative 12 is negative 24 is equal to negative 12c. So c in this case will actually be equal to 2, right? And once I plug this back in, I'll get f of x minus 12 is equal to 2 times x minus, what did we have? X minus 2, x minus 3 and x minus 7. Okay, that's great. Now I just plug in x equal to 0 over here. I'll get f of 0 minus 12 is equal to 2 times negative 2, negative 3, negative 7. F of 0 minus 12 will be equal to 2 to the 4, 12 and 12 sevens are 84. But this will have the negative sign over here. So f of 0 will be equal to negative 84 plus 12. So f of 0 will be equal to negative 72. So essentially the modulus of f of 0 will be equal to 72. Essentially it does not matter what case it is, f of 0, the modulus of f of 0 will always be 72. So therefore our answer is 72. Essentially what is happening over here is we don't really know how the graph of that particular cubic will look like. We don't have enough knowledge to deal with that, right? That's completely in a different domain altogether. We don't know exactly whether the graph will, look something like this, like we discussed in case 2, or it will be the other way around, like we discussed in case 1. We really don't know that. But what we do know is the value of f of 0 will be the 72 or minus 72, depending on what case it is. And of course, the modulus of f of 0 will always be 72. Doesn't matter on what case it is. So yes, that was pretty much the question. And yeah, I really hope you enjoyed that and learned something from it. Okay, so moving on, we have certain book sessions for the AIME and AMC. Mathematics can be fun by Yakov Perelman. Mathematical Circle, The Russian Experience. Algebra can be fun by Yakov Perelman. Excursion Mathematics and Challenges and Thrills of Pre-College Mathematics. And of course, Elementary Number Theory by David Burton. Moving on, a similar but challenging problem. So find out the values of A for which the given cubic has 3 distinct real roots, 2 same root and 1 different root. So this is essentially alpha, beta. This is alpha, beta, gamma, and only 1 real root. So let's just say alpha. The only real root is alpha. It might not, then the rest of the 2 roots will obviously be imaginary. They're not real. And if you're able to make any progress on it or if you're able to solve it, please let me in the comment section below. And until then, I'll see you in the next video. Thank you very much and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.